The last section in chapter 14 is about catalysts. A catalyst is anything that you can add to a reaction that makes it go faster that doesn't actually get used up in the reaction itself. The way catalysts speed up reactions is they lower the activation energy. But when they lower the activation energy, they don't actually change the change in energy or the delta H for the whole reaction. The way that catalysts do this is that they will cause a reaction to occur using a different mechanism. And by providing this alternate mechanism, you end up with a lot more collisions occurring during the reaction. If you were going to look at a graph of this, right, here's our normal graph for a regular reaction. We have potential energy over here versus our reaction pathway. We start out with our reactants, and as the reaction progresses, we need to reach that activation energy to get to our transition state in order to make our products, which are over here. This delta H here is the enthalpy change from the reactants to the products. When you put in a catalyst, you're still starting out with the same reactants, you're still ending with the same products, but what happens is this. You give it a different mechanism, a different pathway for the reaction to occur, and the activation energy, this part, goes down, but the total delta H, our activation energy goes down, it becomes a lot less, but our total delta H is still going to remain exactly the same because we still have the exact same products, we still have the exact same reactants, and so this part right here still stays exactly the same. So it doesn't change anything about the reaction except the rate. That's the only thing it changes in the reaction. Catalysts can be homogeneous or heterogeneous. If they're homogeneous, that means they're in the same phase. If they're heterogeneous, they're in a different phase. One important group of catalysts are called enzymes. You learn about enzymes a lot in biology. These are catalysts that are found in biological organisms like us. We have catalysts, all those little chemicals you learn about in biology or AP Bio that end in ACE, like DNA polymerase and catalase and I don't know all of them. These are all things that help the reactions that take place in our body all the time, that help them go really quickly. The neat thing about these enzymes is they don't get used up at all in the reaction, so our body can keep reusing them over and over and over again. They work using something called a lock and key model, in which they fit into very specific sites based on the proteins that make them up. And if you want to know more about that, go ask a biology teacher because they know way better than I do. Alright, so let's take a look at some problems involving catalysts. Okay, here we have a reaction of formic acid. The red line here is showing what happens when formic acid decomposes on its own. The blue line is showing what happens if you add the catalyst zinc oxide to it. The question wants to know, find the half-life and the first order rate constant, and then it has a second part we'll get to in a second here. So to find the half-life, we can actually just look at the graph. We can just see how much time does it take for half of it to disappear. So if we take a look here, it drops from 300 to 150 in about this amount of time right here, somewhere around here. So what is that, around 750, 600, somewhere around there. So that's going to be our half-life. To figure out the value for K, since it tells us it's a first-order reaction, and since we know it's half-life, we can go ahead and just use that half-life equation that we learned a few sections ago and use that to solve for K. So our equation looks something like this. We can just plug in our value for half-life, which I estimated about 660 seconds in, and then go through and solve for K. And when we solve for K, we get about 1.05 times 10 to the negative third inverse second to the negative 1 power. The question also asks us, suppose we plotted this is plotted in pressure values here. Suppose we plotted this in concentration instead. What effect would this have had on the calculated value of K? It wouldn't have done a thing. You would still get the exact same half-life because the time it takes for pressure to drop in half is the same as it takes for the concentration to drop in half. and therefore you're going to end up with the exact same value for K. The next question asks us the pressure of the formic acid is starting at 300 torr. Assuming constant pressure and ideal gas behavior, what is pressure in the system at the end of this reaction? Well, according to this equation up here, if you're starting with 1 mole of the formic acid, you're going to make 2 moles of gas. So if you start with 300 torr, you're going to end with 600 torr if the reaction goes to completion. So since we're making twice as much gas as we started with, our pressure is going to be twice as much. Next, the question gives us the volume of the container. Wants to know moles, so if we got pressure, if we got temperature, which it gave us up here, we got volume, then we can use PV equals nRT. Since it wants how many moles are at the end of the reaction, we want to use the pressure at the end of the reaction, so 600 torr. Be sure to remember to divide that by 760 to get that to ATMs. We want our volume in liters, so that's 0.436 liters. Remember, centimeters cubed, the same thing as a milliliter. N's what we're trying to solve for. R is 0.08206. Whoops, I forgot the O. And temperature, it told us, was 838. We go through all of this. We're going to get an answer of about 0.005 moles. And then our last question is going to be about enthalpy. It gives us the standard heat of formation of formic acid. It wants us to calculate delta H for our overall reaction. It gives us an assumed activation energy, and then it wants us to do a few little sketches. One thing we'd have to know to be able to do this is we'd also have to know the delta H formation for the other things in the reaction here, and so we'll have to look those up, I guess. So we can use the equation of products minus reactants. If I look up the delta H for formation for carbon dioxide, I get negative 393.5 kilojoules per mole. For H2, it's just 0 because it's an element in its standard form. And then it tells me in the problem the enthalpy of formation for formic acid. And then the delta H of reaction is what I'm trying to find. Go through and solve this. I get negative 14.9 kilojoules per mole. And the reason why this is important to us whenever we try to draw this diagram is that since this is a negative value here, that means when we draw our reaction diagram, we want our overall delta H from there to there to be negative, indicating an exothermic reaction. If I want to show what this looks like with the addition of zinc oxide, I show the exact same reaction, only now with a lower activation energy.